Hello! Have you ever wondered on how to make your own battery? With all the talks of huge leaps in battery technology, this got me wondering if we can make an effective DIY battery that isn't just sticking pennies on a lemon. Most batteries we see in our day-to-day lives uses some form of lithium, which unfortunately means it has a tendency to burst into flames, as well as having a short lifespan. In second place, we have lead-acid batteries, usually found in automotive application, but unfortunately uses lead and sulfuric acid, which are both major safety hazards. After doing a quick research, I have stumbled upon a new type of battery called a zinc iodine battery. As the name suggests, it uses zinc and iodine inside the battery. This battery is interesting since it uses water as an electrolyte, as well as being very durable compared to lithium. But due to the horrible energy density, it will be reserved for power grid applications, so don't expect it appearing in your cars or phone. Now let's go into making the cell. For the container, I will use a polypropylene tub. For the bread and butter of the cell, we will be using zinc as the anode and graphite as the inert cathode. The electrolytes I will be using in this project will be zinc sulfate and 1% iodine solution. For the cation exchange membrane, I will use PVC cement, cation resin beads, and fiberglass. And for the additional electronics, I will be using a variable DC power supply, a multimeter, and some crocodile clips. Now let's go into making the membrane. To do this, I will add the resin beads into a food processor so it can be ground into a fine powder. Afterwards, I mix the crushed resin beads with some PVC cement and let it cure on the fiberglass weave for 24 hours. Unfortunately, this didn't went as planned since the mixture wasn't spread evenly and refuses to stick with the fiberglass weave, so I have to get back to the drawing board with a new design. After doing a bit more research and some experimentation, I think I might have found out a new design for the membrane. Here is the finished membrane made using just a plastic bottle with some holes poked in it. Additionally, I have glued this thing to the bottom of a new plastic container to act as the battery tub. In the meantime, I modified the graphite cathodes with an aluminum crown so it can fit with my tiny crocodile clips. To make the analyte, I will be preparing a 0.5 molar zinc sulfate solution by dissolving around 72 grams of zinc sulfate heptahydrate into 500 milliliters of distilled water. Now let's assemble the whole cell. For this, I'll be connecting the cell in parallel, which will double the current, making it somewhat more usable. Now it's time to fill in the electrolytes, starting with the zinc sulfate solution we have just made before. This will serve as the analyte for our cell. Unfortunately, when I poured the iodine solution, I just realized a fatal mistake, in which the membrane completely fails to block the iodine and causing it to cross over into the zinc side. Despite the efficiency losses from the iodine crossing over, I was able to still clock in 1.1 volts out of this, which is quite impressive. After looking at this mess, I have decided again to go to the drawing board for the second time with a new method, which basically boils down to dividing the cell with a newer membrane design. For this new membrane, I bought another type of fiberglass, grounded up the rest of the resin beads, as well as buying a new can of PVC cement, which is cured for a day. This is the end result, and unlike my first attempt, it doesn't peel apart. After some inspection, I cut the membrane to smaller pieces and started gluing them into the tub using hot glue and finishing it with silicone gasket. Like last time, I wire all the cell in parallel to maximize the already tiny current produced by my cell, as well as prepared another solution of 0.5 molar zinc sulfate to as the electrolyte. With the newly made membrane, iodine is completely blocked from migrating towards the zinc side, minimizing parasitic loss and wasted reagents. With these improvements, now the cell produces a stable 1.17 volts, as well as produce enough current to drive an electric motor. Upon closer inspection, even under load, the current generated by the battery remains stable, which is impressive for such a crude battery. To charge the battery, simply reverse the polarity of the output so that the zinc side becomes the cathode and the iodine side becomes the anode. This is to regenerate the reactants by redepositing metallic zinc at the battery anode and elemental iodine forms in the cathode. It is important to keep the charging voltage around 0.1 volts higher from the nominal cell voltage to suppress water electrolysis and zinc dendrite formation at the anode. In conclusion, we have deduced that this type of battery is feasible, but there's always room for future improvements.